Hi all, and welcome to your next lesson from chapter 14. This time we're looking at 14.3, comparing the cardinalities of infinite sets. So, get yourself ready for notes and we're going to get started. Now, recall from previous weeks is that we know that two cardinalities are equal if a bijection exists between the two. So from A to B. Now, since we're comparing, we're talking about things less than, or greater than. So the cardinality of A is less than or equal to B if an injection exists. And this order does matter because obviously, in this case, we're looking at an inequality. Here, order doesn't matter. The symmetric property means that those are the same. With inequalities, order does, so an injection exists, A to B. And we can also say that A is strictly less than B. So here we're noticing it's less than or equal to if an injection exists. It's strictly less than if an injection exists. And no surjection exists. So here it's enough to prove that there is an injection if it's less than or equal to. If it says strictly less than, we have to also prove that no surjection exists. So in this case, we're looking at, given any set A, the cardinality of A is less than the cardinality of the power set. So here we're looking at less than, so what we want to do is we want to create an injection, show that an injection exists, and we want to show that there's no surjection. So it's going to be two steps. So our first goal is, and this is why it's important to think about it as infinite sets, because if the cardinality of A is finite, meaning that it's equal to a number where n is in the natural numbers, then hopefully you'd recall the power set, which is the set of all the subsets of A, is equal to 2 to the n, and we know that n is less than 2n for all natural numbers. So if it's finite, we don't need to worry about injections, surjections, bijections. So let's say that A is infinite. So as we say here, our first goal is to write an injection from A to the subsets of A. Now, injections tend to be a lot easier to write than bijections, so I'm just going to say, okay, write a function f from A to the power set of A exists such that f of A is equal to the subset containing A. Now, obviously, this is not a bijection because this is missing out on any subset of A that has two elements, 3 elements, 4 elements. So it's definitely not surjective, but it is injective. This is pretty easy to show. If f of A1 is equal to f of A2, that means that these two are equal. So injections are easier to write than bijections. Now, I'm going to clear a little space there. So that's our injection. Now, what we want to show is that we want to show no bijection exists. So, in order to show that something doesn't exist, I'm going to use contradiction. So, what I'm going to say is, suppose a surjection does exist. This is our, we're trying to prove the opposite. Exists. And it's going to be a different function than the one above, because that's definitely not a surjection, as I said. But let's say one exists. So what that means is that every set has an element of A. So if I take X is a subset of A, since there's a surjection, what that means is that implies that there is some element of A where f of A is equal to that subset. So all the subsets have a buddy. Basically, we can think about this as it's pointing towards that in the function. Now, consider, I'm going to give you a new set. B is a subset of A such that B is equal to the set of all the elements of A where A is not in its subset it points to. So it's, obviously sort of the opposite of this. So B is the set where it's full of all the elements that aren't in the subset it points at. So if, for example, A isn't in X, A would be in B. Now, this is where we get our contradiction. So we've got two options. So let's say that because we have a surjection, there has to exist some element of A that's equal to B. B is a subset of A. It's surjective. This is true. Now the question is, where is the element X? So if X is not in B, what this means is that X is not in f of X, since those two are the same set, which would, of course, imply, but then if X isn't in f of X, then X must be in B. If X is in B, the reverse is also true. If X is in B, that means X is not in f of X. And if X is in f of X, that means that X cannot be in B. So here's our contradiction. So therefore, then no X in A exists such that f of X is equal to B, and we don't actually have a surjection. So since an injection exists and a surjection doesn't, the conclusion we must draw, hence, the cardinality of A is strictly less than the cardinality of its power set. And this is a really helpful idea that you can use in some of your later proofs, is the idea is that if you can write something between a set and its power set, you know that this is going to be less than. It's also a helpful comparison so that if you have a set and you have something that would be really easy to compare to the power set, using an injection or using a bijection, that can be a really helpful tool as well. Don't be afraid to throw in a third set. So here, number 2, show that the natural numbers are less than the real numbers. So again, we're going to show that we have an injection. And again, generally our injections from here to the reals are pretty straightforward. So in this case, I'm just going to say the natural number is just equal to itself. I changed the variable on you again. Just equal to itself. Now this is a very obviously injective, and it's very obviously not surjective because we're only counting the natural numbers in this function, right? Natural number to itself. Now our goal is we want to show that there's no surjection. And again, we're going to consider contradiction. So what that means is that we're going to say that f of X from the natural numbers to the real numbers exists where f of X is surjective. Now, the way I have best to illustrate this contradiction, I find, is with a table. So let's imagine what this could look like. So we have our natural numbers and then our function of real numbers. So 1, 2, 3, 4, 5, etc. And these real numbers, and they could be anything you want. They could be 0.010101, go on forever. This could be 7, just the number 7, which would have infinite decimals like that. This could be, 2.317861. I'm making these up. This could be our old friend 3.141592. Here we could have negative 1/3, right? These are all real numbers, and these would keep going forever. This is what an example would look like. Now, what we're going to do is just use this to illustrate a point. So I'm going to consider an element of the real numbers where the 10th place, so here, the 10th place is not equal to the 10th place of f of 1. So whatever, it maybe means that this is the x value, and it just means that 0 can't be the first number. So maybe x in this case can't have 0 as the first number, so I'm going to say it's got 2. The next time I'm going to say that the 100th place is not equal to the 100th place of f of 2. So again, it can't be 0, so these have to be different. So again, that digit's 0. I'm going to say that in x it's 5. It just has to be different than 0. It's not going to match the thousandths place of your next number. So instead of 7, I'm going to say it's 8. It can't match the 10,000ths place here, so I'm going to say it's 0, because it just can't be 5. For the next one, it's going to go to the next place, so it just can be anything other than 3, so I'm going to say 1, and so on. So this is how we're going to create an element of x. So it has all these digits that are different. All these digits that are different from each of the numbers going down. So what this tells us is that x cannot be f of 1, x cannot be f of 2, x cannot be f of 3. So what this says, x cannot equal f of any number for all n in the natural numbers, since its 10 to the negative nth digit is different. Maybe all of it is different, but at least that one's different for every single space. And so, therefore, x is not in the range of f of. So, f is not surjective. Now, this is a really important one, and this is a really important method to be like, oh, well, it's different here, it's different here, it's different here, it's different here. If it's different in all of these places, that means it cannot be a part of that function. Our last example is prove or disprove. If U is a subset of A and U is uncountable, that implies that A is also uncountable. So just like before, if you're proving something's uncountable or something's not true, we're going to want to use contradiction. So I'm going to start out by saying, so say that U is a subset of A and U is uncountable, but A is countable. So, now, what this says is that if U is uncountable, that implies that U is infinite, which would mean that A is infinite, since A contains all the elements of U. Right? Now, since A is infinite and countable, so therefore what that means is that A is infinite and countable. That means that A has, A1, A2, that's the countable part. And the infinite part means that it has 1 for all the natural numbers, right? But we know that then U is, since U is a subset of A, so that implies that U is equal to some set of the A sub i's for where I is in a subset of the natural numbers. So think about subsets. Maybe U has 1, it has A sub 3, A sub 4, A sub 9, A sub 307, some subset. That's its definition. Now what this means is that the cardinality of U is equal to the cardinality of that subset. However, X is a subset of N, so by definition, that is countable. So X is countable. Plus U is countable, which is our contradiction because we started off with the exact statement that U is uncountable. Therefore, A is uncountable. All right. Let me know if you have questions about the ideas of less than or equal to or strictly less than in terms of cardinalities, and I'll be available by email, on Zoom, or in the comments.